Right. Assalamu alaikum. So we're going to start with the Ohm's law. So I'm just going to put this in an inverted comma. Ohm's law for fluid, and our fluid, of course, is blood flow. Now, suppose we have a pipe. This pipe could be an artery through which blood is gushing forward. The radius of this pipe is capital R. We already know that if the fluid has some viscosity or some friction, then an external agency is needed to make the flow possible. So if you look at the Ohm's law, we have a voltage difference across the ends of a wire, which enables a current to go through the wire, and there is some resistance to the current flow. Exactly in an analogous fashion, across a small segment of a pipe, we need some pressure difference, some delta P. So in analogy to delta V, we could write delta P. In analogy with the current, we have flow. Let's denote flow by Q. And we must have something analogous to resistance. Let's call this the resistance to the flow. Okay. And if you look at the units here, this of course is in pascals, in SI units or millimeters of mercury. Q has to be in terms of some volume unit per unit time. And this resistance has to be in some units, and you can find out what the units are going to be to make this dimensionally consistent. Pascal is Newton per meter square. All right. So let's work out this problem from the perspective of physics. What is the analogous quantity to resistance? But before we move on to that, I would like to recall the concept of stress and strain. Suppose I have a solid object. There is some dimension y, and to this object, I apply a stress, sigma, which is analogous to pressure, Newton per meter square. And as a result of this stress, this object compresses. And there is some change in its dimension, and that change is delta y. Now, if this object is elastic, then we know that the strain in this object, which is defined as the change in its dimension with reference to some other dimension, y, this is the strain in this object. This is going to be proportional to the stress. Correct? This is called Hooke's law. The stress and the strain are directly proportional, and you can insert some proportionality. Let's call it the Hooke's constant. Okay. So this is true for a solid, an elastic solid, the simplest solid that you can think of. You apply a stress to it, and a strain develops in this object. Exactly for fluids, we have a similar situation. We have a pressure, and we have some quantity which is analogous to stress, and we have some quantity which is analogous to strain. Now, if you look at this pipe here, now I'm going to draw another view of this pipe. So I'm going to do a longitudinal section of this pipe, and these are the walls of the pipe. And now I consider my fluid, which is blood, and I take a particular point in this pipe. This object, this particle here is moving with some velocity. It's possible that a neighboring particle is moving with another velocity. And these velocities could be different. It's also possible that at the walls of the pipe, the object is static. All right. This is called the no slip condition. So we're putting in some assumptions in place. So there is a distribution of the velocities along this pipe. All right. Now, if I look at the axis of this pipe and define a parameter, which is the distance from the axis of the pipe, then this velocity is going to be a function of r. So the particles are now moving with different velocities. And this is what happens in a real Newtonian fluid. Now, what we would like to do is we would like to come up with a relationship similar to what we have for the stress strain relationship in solids. Now, if you observe carefully, and if I were to draw a small section here of fluid, there is a force that is acting on this fluid that is tending, that is parallel to the surface of this section. Here, the stress was normal to the section. In a fluid, if you were to make this object flow, you have to apply a force that is parallel to this section. All right. Now, if you, in such a case, you define another kind of stress. That stress is called shear stress. So if I have a section of a solid or a fluid and I apply a force in this fashion on one surface and a force on in this fashion on the other surface, then this object is going to shear. So a shear stress is going to apply in this object. All right. So the new position, the new configuration of this object could be slightly slanted. A rectangle could be transformed into a parallelepiped. All right. Now, in fluids, you don't want to talk about stress in that fashion, compressible or tensile stresses, because your fluid is incompressible. The fluid is rather moving along the axis of the pipe. So you have to consider forces that are coaxial with the pipe. And those forces also act on certain areas. All right. Therefore, you could define a shear stress, which is force per unit area. And this is denoted by tau. And how do we define this tau? Let me draw this section of the pipe again. And now I would move back to my perspective drawing. Here is my pipe. Here is my hypothetical axis of the pipe. And now I take a small pipe within the pipe. And I make this three-dimensional. So this has a certain thickness. This distance is r. The inner wall is at a distance r. The thickness of the pipe is dr. So the outer wall is at a distance r plus dr. This length of this small section, which is I'm considering within the larger flow, is suppose dz. So now I have an annular pipe, a hollow pipe inside the big fluid flow, and I'm considering only the element of the fluid inside this annular pipe. And now I have shear stresses, a shear stress tau being applied to this amount of water, to the water inside this annular ring, tau. All right. So I have tau proportional to some strain. Stress is proportional to strain. Now we have to define what the strain is for this case. Now, if you're looking at flow, you want to define the strain in a fashion that is slightly different from what you've defined in the solid. You need to take into account the rate of strain. How does the strain change with time? Because that allows a fluid to flow. All right. So now how would I define that? I would define that by taking the v is the speed, which is a function of r, and I would like to find out how this changes with the radius. So what is the strain doing here? The strain is moving different layers of the fluid with respect to one another. That's what the stress is doing. It's going to displace, if you break up this fluid into different horizontal sections, what the strain is trying to do, it is trying to displace the different elements with respect to one another. This is how the fluid is going to flow. So you have to find out what the speed of each layer is at a distance r, and then you would have to differentiate it with respect to r. So what is v here? V really is the displacement with respect to time, the time rate of the time rate at which a layer is moving at a distance r. All right. So I could come up with a relationship exactly analogous to the stress strain relationship for the solid. Tau, the stress, the shear stress, is now proportional to the rate of change, the spatial rate of change of speed. And I can put in a constant of proportionality. This constant of proportionality is generally called the viscosity. Remember that this VR is really dz by dt. How does the fluid advance in the z direction with respect to time? All right, now if I were to plot a graph between tau, which is my shear stress, and my rate of strain, which is d by dr, dz by dt. I could also write this. Why am I calling it the rate of strain? Because if I define strain as dz by dr, what is dz by dr? It's a strain, isn't it? Let me just mute a participant. What is dz by dr? dz is the displacement of a fluid, of a layer of fluid, and r is a characteristic length scale in this object. So if I consider a layer here, this is moving through a displacement dz, and the characteristic dimension of this layer is this distance r. That's exactly what we have over here. How do we define strain? It's the change in a dimension referenced with respect to a reference dimension, y. That's strain. This is how we are defining the strain over here as well. The change in the position of a layer of fluid, dz, with respect to a reference. And now for fluids, we would like to put in a time derivative as well. So this is indeed a rate of change of strain, right? So we're trying to look at the Hooke's law for fluids. So what we've done is we've replaced the strain in a solid with the rate of change of strain. And we've replaced the compressive or the tensile stress with the shear stress, because it's the shear stress that is making the object move here. All right, so if I were to make a plot between these quantities, yes. Yes, dz is analogous to dy, delta y, and r is analogous to y, right? Strain is how does an object change with respect to some scale of the object. Here, the scale of the object is how far are you from the axis of the pipe. That is defining the scale of this problem here. Now, if I were to make a plot between tau and this object, what am I going to get? what is this graph going to look like? Straight line. If eta were a constant, this is going to look like a straight line. So if the viscosity does not depend upon how much strain you apply, then this is an example of what is called a Newtonian fluid. G, because this is some variable tau is proportional to this variable. Two variables that are linearly proportional to one another, they're represented by a straight line. If this eta is constant, if this eta does not depend upon the rate of strain. So these are Newtonian fluids. An object, a fluid can act in a Newtonian fashion in certain conditions and non-Newtonian fashion in certain conditions. You can have different kinds of objects, and that's why fluid mechanics is such a rich subject. You can have objects in which the slope goes up as you apply more strain. You can have objects in which the slope goes down as you apply more strain. So you can have shear thickening and shear thinning objects like ketchup. You apply a little bit of stress, it doesn't flow. You apply more stress, it starts flowing. Toothpaste. So these are non-Newtonian fluids. You can also have an object that does not show any strain up till a certain point, and even only if the stress goes beyond a limit, it starts to flow. There are different kinds of fluids, but blood, for example, the rheology of blood is really complex. So blood, if you look carefully, is about 45% of blood is plasma, and 55% of blood is cells. Most of them are RBCs, about 5 million in a cubic millimeter, red blood cells. 95% of the cells are red blood cells. So they make blood, the viscosity of blood very complex, and blood is generally a non-Newtonian fluid. But in certain cases, we would like to consider Newtonian flow. So what the assumptions that we're going to make in order to derive the Ohm's law is that we have the no slip condition, which means that at the walls of the tube, the blood is static. We also have blood, we're considering blood in a Newtonian setting, which means that the viscosity does not depend upon the rate of strain. And that is only true when the rate of strain is large. And we have laminar flow, non-turbulent, which means that the speeds are slow enough. The Reynolds number is low. So we're considering certain conditions in which this Ohm's law is valid. And this is generally found in large arteries, not the aorta, but in the larger arteries. For example, the artery in the arm, the brachial artery. All right. So now let's move on to this problem again. So if I look at this small section and I would apply Newton's law to this small section, I can derive my intended Ohm's law. So let's do that. So this is my big pipe, the artery, and I have a small section within it of a certain thickness, BR. All right. Now the pressure here is P. The pressure on this section, let's call it P plus dP. And there is some shear stress, let's call it tau, that is trying to make this nice cylinder, make it slightly slanted. Now, if this object is in equilibrium, which means that this parcel of fluid is not accelerating, the speed is constant, then the net force on this parcel of fluid has to be zero. That's a condition for equilibrium. So let's look first of all at the rightward forces and equate them to the leftward forces. All right, so this radius is small r. So could anyone tell me what the force is going to be? Let me, sorry, change this as well. Sorry, I need to get used to this. So what are the rightward forces acting on this wall? Force is pressure into area. So P, so what's the area of this section? So if I look at this section from the left, this is what I observe. This radius is R, this thickness is dr. So what's the area that I'm considering on which the force P is acting or pressure P is acting? What's this area? It's not pi r square. It's like a curved rectangle. No. So what's the thickness of this rectangle? Dr. What's the length, circumference of this rectangle? 2 pi r. So P 2 pi r dr is the force that is acting due to the pressure that is acting on this annular region, right? But I also need to consider the forces that are acting due to the shear stress. Could anyone tell me what the shear stress, what those forces are going to be if this length is dz? So in order to calculate a force, I need to multiply stress with the area. Now my stress, shear stress is tau. What area do I need to consider? Is it this area that we need to consider? What is my relevant area over here? These forces due to these shear stresses, on what length are they acting? They're acting on the walls of the cylinder, right? Because they're parallel to the walls of the cylinder. So it's the lateral length of the cylinder that you need to consider. So what is the area of the curved surface of the cylinder, of this small cylinder, this infinitesimal cylinder? क्या area होगा उसका? Exactly, 2 pi r dz. So these are the rightward forces. Now you need to equate this to the leftward forces. So these are my right forces. Now I'm going to write down the leftward forces. So the pressure has gone up, P plus dP, 2 pi r dr plus all right. So now what you would like to consider is, if I look at this cylinder. So let me ask to draw your attention to this cylinder. So if you look at this tensile, this shear stress on the inner wall, the forces are acting to the, we are assuming that the forces are acting to the right, and on the outer wall they are acting to the left. Okay, so here the force due to the shear stress is acting inward, and here the force due to the shear stress is acting outward, which is tending to disfigure the skin of this parcel. So this force over here is really acting on the inner surface. So if I were to draw the inner surface, just the inner surface. Tau 2 pi r dz is the force that is acting on the inner surface of this annular ring G. Uh, you could do it the other way as well. All right. So what we are assuming is that the flow is from the left to the right. And we already know the solution that inside the towards the axis of the cylinder, the fluid is moving faster. So that makes more intuitive sense to consider the shear forces inside the cylinder to be acting towards the right. All right. So ये बात समझ आ गई? So now we have a cylinder and we're trying to have forces in the inner periphery of the cylinder acting towards the right. And the forces are the shear stress multiplied by the area. This distance is r. So this circumference is 2 pi r. And you multiply this with the length dz, you get the inner area. All right. Now, if you look at the forces that are acting to the left, you have the forces due to the pressure, but you need the forces due to the shear stress as well. So what you would like to do is the shear stress is tau 2 pi. Now, on the outer periphery of this cylinder, the shear forces are acting towards the left. All right. And the distance of the outer periphery, which is now drawn in pink over here, is r plus dr. So what you would like to do is replace this r with r plus dr and put a dz as well. Okay, you create the right part hand of the equation with the left hand equation. Some terms are going to cancel out. Now, if I were to do all of this calculation, let's do it. So P 2 pi r dr plus tau 2 pi r dz. Okay. By the way, this tau also has to change to tau plus d tau. Okay. The shear stresses could also be different on the two sides. So this is the left hand side. The right hand side is P 2 pi r dr plus 2 pi r dp dr plus tau 2 pi r dz plus tau 2 pi dr dz plus 2 pi r d tau dz plus 2 pi d tau dr dz. All right. Got it? So what we are assuming is that this tau here is going to be different at different heights. All right. So this is entirely general. So on the right hand side, if you look at the outer periphery of this wall, this tau has to be replaced by tau plus some d tau. All right. So this is just algebra from here onwards. So this is just going to cancel. This is just going to go away. This term is going to go away. And now we would also like to ignore this term because this is a product of three small quantities, d tau, dr, and dz. We assume that our cylinder is really small. So this thing we also ignore. We only keep terms that are second order in small quantities. Now, if we do all of this, we get 0 equals 2 pi r dp into dr. So this term, I'm going to write this term here. Now, instead of dp, what I would like to do is I would like to write this as dp over dz dz. So this is just the first order term in the Taylor expansion. A small change in p is equal to the rate of change of t with respect to length multiplied by the small length. Chain rule. So then I move on to plus tau 2 pi dr dz plus 2 pi r. Now instead of dt, d tau, I would like to write how does the shear stress change with the radius? And then apply a chain rule again. The first order term in the Taylor expansion. And this is what I'm left with. You get this? Now I take this term to the other side. I get minus 2 pi r dp over dz dz dr equals tau 2 pi dr dz plus 2 pi r d tau over dr dr dz. All right, so far so good. So fortuitously, these terms just go away. I can also get rid of the 2 pi. Finally, I'm left with minus r dp dz equals tau plus r d tau over dr. Now, can I write this as, can I convert these two terms into a single derivative? So this is a derivative multiplied by something plus some tau, which can be a function of r, by the way. Can I write this as a single derivative of something using the product, what you call the product formula in calculus? क्या लिख सकता हूं मैं? The spatial derivative of tau r. Tau by tau r. By the way, remember that tau is a function of r. So you can tuck in a small argument in tau as well. So this is a single derivative. All right. Now what I could do is I could integrate both sides of this equation. If I were to integrate both sides of this equation, I would have it tau r equals. Now dp over dz, what is this term? How does the pressure change along the length of the pipe? This is like a pressure gradient, isn't it? So you already have a semblance of the flow has to do something with the pressure gradient. How does the pressure change with distance? And this is a constant. Suppose this is a constant. This does not depend upon radius, about how far, what point in the cross section of the pipe you are at. This, right? So this is just a constant. Now this is a variable. You're integrating with respect to this variable, right? So what you're really doing, if you want to do this step, integrate with respect to r, the right hand side, tau r, and here you are minus dp over dz. This goes outside the integral. This is what you're going to do. Okay, so if I were to do this integration, I've got a minus sign, dP by dz, which is a pressure gradient, a constant. And what is the result of the integration of r? R square, right? So this tau as a function of r is really minus r over 2. What does this show us? So how do we interpret this? Can, in simple language, can you explain what this is going to mean? इसका क्या मतलब? Yes, please. Right. So along the length of this pipe, so now I'm going to draw the big pipe. Let me draw this in plan view. So this is a longitudinal section of my pipe. This is my central axis. What that particular equation is showing is that the shear stress tau is not constant along this section. It's variable. It depends upon how far you are from the central axis. And if I were to make a graph, here I put, this is my r axis, here is my tau axis. My stress is 0 on the axis, and it's maximum as I move towards the wall. So I could make this particular kind of graph here. Okay, so this is above the axis, this is below the axis. Forget about the negative sign for the time being. It's going to be in one side on one end, right? R is just a radial distance, is always positive. So the stress is non-uniform. The shear stress is non-uniform. The shear stress is maximum on the walls, and it's 0 over here. Got it? That's why if I were to look at the velocity profile of this fluid along the pipe, the velocity is more likely to be high in the center of the pipe. It's going to be 0 here under the no slip condition. Remember, we're talking about a Newtonian fluid in the laminar flow region, slow speeds, not very viscous. So these are arrows, in the intended arrows for the velocity profile. This is what they might look like. The shear stress is 0 here, no slip condition. The fluid does not move along the walls. And we can make a waterfront, like a wave front for the fluid. So in laminar flow for a Newtonian fluid, blood inside one of the big arteries, not the aorta, but smaller than aorta, but the big arteries, blood is going to flow like this. But this flow has to develop. It does not develop instantaneously. It has to develop over time. So this is what happens in the steady state. And once it does that, it does not accelerate. This velocity profile just moves forward. Okay, but this flow has to develop. The development of this flow requires some acceleration, by the way. So once in steady state, this flow has developed, the shear stress is maximum here, minimum here, 0 here rather, and the wavefront develops. Now, what is the shape of this waveform, of this wavefront? This is something that we would like to see now. In other words, what is the form of VR? How does the speed change with R? Yes, please. So this is a quasi-static condition. If you look at this fluid front at some later time, this entire front will have moved towards the right. So here again, at this snapshot in time, the fluid will be static here. So this is a quasi-static flow, very slow. And this entire wavefront is moving ahead in time. If you take a camera which can measure velocities, that's what is called a Doppler camera. If you measure the velocities, the velocity at this point, at this instant in time is going to be zero. Look at a pendulum. When the pendulum reaches its extreme position, it's static there. Then the pendulum still moves, right? Now, could you tell me how the speed is going, what the speed is going to look like? How can I find the expression for VR? So we already have the shear stress. We already have the Newton's law for Newtonian fluids. How does VR going to look like? How will you find out VR? We resort to this expression over here. This is the Hooke's law for Newtonian fluids. We have a relationship between tau and the derivative of the speeds with respect to r. So we plug in the tau that we found into this expression and find out, we get a differential equation that we would then like to solve. So tau is now given by that expression over there. This is tau. This must equal eta dv over dr. Now solving this is peanuts. You would like to integrate both sides with respect to what? Integrate this with respect to r. Integrate this with respect to r. So I'm just going to put the right hand side, make it the left hand side. Eta d so this will just become eta vr, correct? Eta vr, because this is going to be the integral of dv, which is just v, equals minus 1 over 2 dp by dz. This is just a constant. What is the integral of r? R square by 2. So I make this 4. Plus I need some constant of integration as well, right? So my speed is minus 1 over 4 eta dp by dz r square plus some constant of integration. Now, isn't this a parabolic expression? So if I were to look at the locus of these points, the locus of the tips of these velocity arrows, I would get a parabola. This is where we finished our previous lecture. The speed as a function of how far above or far below the axis of this artery is a parabolic function of r. So all the levels inside this artery of blood, they're not flowing with the same speed. All right. Now, our goal is to get to the Ohm's law. Right. So it's a long, tortuous journey still. But all these bits and pieces are coming together. How can we find this constant of integration? I hope this is not your first encounter with a differential equation. Yes, please. Exactly. So what is that condition? So 0 equals minus 1 over 4 eta dp by dz capital R square plus c. So far, so good. So This becomes positive. This is my C. Now, if I were to put everything together with this boundary condition, this is called a boundary condition. With this boundary condition in place, my velocity field, my velocity profile will look like 1 over 4 eta dp by dz r square minus capital R square. Sorry, I'm sorry. Capital R square minus small r square. Or this is my velocity profile. ये मैं इसको नीचे ले गया हूं. Sorry. All right. So all of this is a constant. By the way, the maximum speed is at small r equals 0 along the axis. So this term goes to 0. This term goes to 1. This is the maximum speed here. So I can write this as V max 1 minus small r over capital R square. Now this dp over dz is a pressure gradient. Now we're getting to the Ohm's law. We're getting there slowly. Now, how do we find out Q? The total cardiac output, the total flow, how much blood flows per unit time. Right. So by looking at this problem, the geometry that we have over here, is it possible to find out the amount of the volume of the parcel of fluid flowing per unit time? How do we find out the amount, the volume? The volume is the area into the speed, isn't it? So Q equals area into the speed, right? Because the speed is distance over time. So area into distance is volume. So in order to find out the small volume of blood that is carried inside this parcel over here, this infinitesimal annular cylinder in here, the volume of liquid inside this object is going to be this cross-sectional annular ring 2 pi r dr into this length dz, and you divide dz by time, you get speed. So the speed in this region is v at r. So in order to find out dq, you would need 2 pi r dr into vr. Correct? This is the amount of fluid in cubic meters that is passing through a certain section per unit time. Any questions? You look slightly confused. Is it making sense? So how do you find out the flow rate? The cross-sectional area into the speed, because the speed is really distance over time. So area into distance becomes volume. So this is, if this is correct, this is correct. Now we're talking about how much fluid is carried by the small infinitesimal volume that we focused our attention on. And that therefore is dq. Now, if I were to plug in the values, 2 pi r dr Vr, I already know is capital R square 4 eta dp over dz. Now I can resort back to this expression over here if I choose. So if I were now to find out the total flow rate in the entire cross section of the pipe, I would need to integrate this with respect to what? R. And what would be the limits? So is that correct? So R should go from 0 to capital R, because we're already considering the surface of the cylinder above and below the axis, right? R is like a polar variable. So I can integrate all of this. So if I do all of this properly, 2 pi R over 4 eta. Now let's move back to this expression, R square minus small r square dr. I would get, let me just reproduce the result over here. I would get pi okay. So this is Ohm's law. Now let me write this expression in its full glory once again for you to ponder upon. And we look at some of its implications in the next lecture. I also wanted to cover Bernoulli's principle here because it applies to heart valves. Remember that today and probably half of the next lecture, I'm going to take a zoom in view of the different parts of the circulatory system. Later, we have to take a zoom out view of how the pressure works in the entire circulatory system. But these are the bits and pieces that go together, that have to be stitched together to build and weave the entire story. So now I have Q equals dp over dz multiplied by this expression, which is pi r4 over 8 eta. I can recast this as dp over dz equals q into 8 eta over pi r4. This object here is the resistance to the blood flow. Let's call this R with a small subscript F. What is the driver? The pressure gradient. Higher the pressure gradient, higher will be the flow. All right. The amount of blood transferred per unit time will be higher if the pressure gradient across a section of the vasculature is large. And there has to be a resistance term as well. That resistance to flow arises because there is shear stress within the liquid. That shear stress is like a frictional force. This frictional force has to be overcome, and it's overcome by the pressure gradient. If blood had no viscosity, the pressure gradient wouldn't be needed at all. Now, if you look at this resistance, the resistance depends upon the viscosity of blood. But remember, we have to remain in the Newtonian regime for this analysis to work. The rheology of blood is really complicated. And it's inversely proportional to the fourth power of the radius of the artery. So if you have an artery in which there is plaque on the inner walls, So cholesterol is deposited on the inner walls, a condition that is called arteriosclerosis. Then the effective radius through which this pipe, through which this blood is flowing, is decreased. And it's a fourth power of R. So you decrease R slightly, the resistance goes up by 1 over the quadruple power, sorry. Right? So it's very sensitive dependent. So for the same blood to go, for Q to remain constant, for the blood, because this determines how much oxygen is needed downstream. For Q to remain constant so that your body parts get the appropriate amount of oxygen, this pressure gradient has to go up. There's a control mechanism which makes the pressures go up. The gradient has to go up so that blood can flow through these high resistance arteries. The same principle applies when you would like to dispense a drug through a very tight needle. You have to calculate what pressure gradient is needed if you know the bore of that needle, so that then you can know how much force is required. So this is the Ohm's law for blood flow. And I will give as a homework problem, what's the average flow rate? Right, so you can find out what the average flow rate is. If I were to take the cross-sectional radius of this artery, pi r square, and I define an average flow rate C, then this equals, I equate this equal to Q. Q comes from here. I can find out what the average speed is, the effective average speed of the blood flow is at a particular section. The resistance, of course, depends upon the viscosity of blood as well. And the viscosity is highly dependent upon the fraction of cells, the proportion of cells inside blood. But the key factor is that it is highly dependent on the fourth power of the radius inverted. Now, the next lecture, I'm going to give you an overview of Bernoulli's equation and see how it applies to heart valves. Then I will give a big picture view of the circulatory system. How do pressure changes across space from heart to head, from heart to toe, and how does it change with time? Because blood flow is not a continuous steady flow, it's pulsatile. It happens in pulses. And what is blood pressure and how do we measure blood pressure? So I'll bring some equipment into the classroom. Hopefully our classes will go as intended and there's no uprooting of the classes, but Allah knows better. So I'll bring some equipment and we'll look at some oscillations of an artery that generally one just bypasses when we do a blood pressure measurement. Right, so we're going to have a classroom demonstration inside the next class, hopefully as well. All right, thank you very much.